morning. Welcome to CDT number 35, and we will be looking at numerical problems on RLC circuits. In the last lecture, we have seen theory on response of RC, RL and RLC elements when subjected to single phase AC supply. And we have seen that for generalized, if we consider that RLC elements are present, the total impedance is given by R plus J omega L minus 1 by omega C, or R plus J XL minus XC, where XL is omega L, XC is 1 by omega C, where omega is 2 by F, where F is the frequency of the supply, and current is given by V by Z, and the power factor is given by cos of tan inverse of R by magnitude of Z. These are the generalized expressions which we have gone through in our last class. Sorry, tan inverse of X by R, right? These were the generalized expressions which we have gone through in the last video lecture. This X indicates either XL or XC, or if you do have both, XL minus XC. Okay. Now, having said that, today we will discuss numerical problems on determining the response of RLC circuits when they are excited with single phase AC supply. So I will start with a basic problem. See, in this problem it is mentioned that a coil is having a resistance of 7 ohms and an inductance of 31 millihenry and is connected to 230 volt 50 hertz supply. So let me draw the figure. This is the resistance and this is the inductance, and it is connected to an AC supply. This is 7 ohms and this is 31.8 millihenry. This is L, this is R, and this is 230 volts 50 hertz, which means it is voltage RMS value, and this is frequency. Now what they are asking us to determine the circuit current, which means I, the phase angle of the circuit current, which means they might be asking us magnitude of phi and also angle of phi, and power factor, which is cos phi, and the power consumed, both P and Q. I forgot to mention, power is consumed, the active power, it is VI cos phi, and reactive power, it is VI sin phi. Okay, these two you will be you should calculate. Okay, now 1 minute. If you see, I have already drawn the circuit. Now this will give you the value of resistance. So this is R, this is L, this is voltage RMS, and this is my frequency, right? So given the terms, it is an RL series circuit, and the resistance and inductance for these, and the source voltage is this one, and the frequency is this one, right? So if I do have this one, what is the angular frequency or speed, what we call it as? It is omega is equal to 2 pi r, isn't it? Which is equal to 2 into 3.14 into 50. So I'll be getting 314.15 radians per second. Okay, this is my angular frequency, omega. Now once we do have this, we will proceed to our each and every factor. The first one is the circuit current. So let me draw the figure again. This is my resistor and this is my inductor. This is R, this is L, and this is my 230 volts 50 hertz, right? Where omega is 314.15. We have calculated it. Now the first one is the circuit current, right? Current. What is current? We have already seen V by Z. What is V? It is V at an angle of 0. If I take here RMS, I'll get here RMS. Okay, by magnitude of Z at an angle of phi. That's it. Or otherwise I can write it. See here. This is VRMS at an angle of 0, which is my 230 at an angle of 0 by Z. In this case, Z is only having R and L. So first let me calculate Z. It is R plus JX minus XC, right? So R is there, 7 plus J. XL means what I should use? Omega L minus 1 by omega C. There is no capacitance in the circuit if you see. So that's why I'll be limiting myself to, this is 314.15 into L is 31.8 millihenry, which means 0.0318 minus 0. So whatever the value you will be getting here, this is here 314.15 into 0.318. This is my imaginary value, this is my real value, this is my inductance. Once you do have this inductance, this is in rectangular form, you can convert it into a polar form. Okay, now I have done the calculations for you. Yeah. So this is my, this is J 314.15 into 0.0318 plus 0. So I'll get 7 plus J10. Okay, now this 7 plus J10, this is Z is equal to 7 plus J10. You can convert it into polar form with the help of your magnitude. If you do have calculation, you can do it very quickly. Okay. Now what is my I? It is V by Z, right? V was 230 at an angle of 0. And this is 7 plus J10. It is also to be converted into angle. Right? Magnitude and angle. And see. If I convert this into magnitude angle, what I have get is 12.2 by 55 degrees. So magnitudes they get divided, 230 by 12.2, I'll get 18.85, and this is minus 0 minus 55, it is minus 55. Okay, right? So this is the magnitude of currents. Okay, 18.85 amperes, and this is the angle of currents. How much it is? Minus 55. Okay. Now, if I move on to the power factor. Power factor, as already I told, V is at V at an angle of 0. I have got it 230 at an angle of 0, right? Now I have obtained what was the value of I? It is 18.85 at an angle of minus 55, isn't it? If I do have these things, if you carefully see, my phi is cos of angle difference between these two. This is 0 and this is minus 55. So what I'll get? This is cos 55. Right. So cos 55, I'll get some value. So this is power factor. This is cos phi. Okay. So this is value. And now whether it is leading or lagging. So if you carefully see, voltage is at 0, current is at 55, minus 55. Which means this is the voltage and current is lagging by 55. So which is lagging? Current is lagging. So that's why if current is lagging, what I told you, power factor is also lagging considered. If current is leading the voltage, then the power factor is considered as leading. So it all depends upon whether your current is lagging or leading. So in this case, since current is lagging when compared to your voltage, your power factor is considered as lagging. See, what is the power factor? Cos of 0 minus of minus 55. Cos 55 it is 0.5735 and should be written as clearly lagging. Now what is the power consumed now? The power consumed, as already I told you, if I want active power T, I should go with VI cos phi. both are magnitudes only, okay. V magnitude RMS value into IRMS into cos phi. What is VRMS? It was 230. IRMS is 18.85 into cos 55. The angle between these two. Cos phi is the power factor, okay. The angle between these two. What is the value? I am getting as 2486.74. Q, it is VI sin phi. I should get only the magnitudes, okay. Use only magnitudes, not the entire complex variables. 18.852. If I do have cos phi, I'll get sin phi also. So what I have got? How to get sin phi? Sin phi is square root of 1 minus cos square phi. Okay. So I'll get sin phi, which is 0.8191. So I have got 3551.43. Yeah. Understood. This is the way how we do the problems. We have seen circuit currents, we have seen phase angle, we have seen power factor, we have seen power consumed. But let me take so sometimes you will be asked to calculate the voltage drops across individual elements. Okay, so what they will be asking is voltage drop across individual elements. Across individual elements. Now what does this mean? Now your circuit was like this, right? R and L, and this was your, right? Your supply voltage was 230. Your current was somewhere around 18.85 at an angle of minus 55. And this was your resistance and this was your reactance, isn't it? So what was the impedance of this element? It was R. And what was the impedance of this element? It was JXL. Now they are asking you to determine the voltage drop across individual elements. So in that case, what I'll be writing? Voltage drop across supply. It is already given. It is 230 at an angle of 0. Now the same voltage drop across resistance. Across resistance. You know, across resistance it is I into Z, where in this case my impedance is only R. Okay, impedance is R. Do remember, voltage is equal to I into Z. In this case, across resistance the impedance is R, so it is R. I value is 18.85 at an angle of minus 55 into resistance value is 7 and its angle is 0. If it doesn't have any angle, it is 0, right? So now, if I multiply these two, 18.85 into 7, let me multiply. So it is 131.95 volts, and the angle is, I'll add angles and just multiply the magnitudes. It's like minus 55 degrees. Now if I want voltage drop across inductance, it is again Iz, but here in this case it is j omega L. Right, so it is 18.85 at an angle of minus 55. J means 1 at an angle of 90. Try to remember this one. J means 1 at an angle of 90 into omega. Omega L means, see, omega is 314.15. L is 31.8. So if I multiply them, I'll get 314.15 into 0.0318. So I'll get somewhere around 10. So into 10. So I'll get, this is 10 at an angle of 90. This value is 10 at an angle of 90. See, for resistor I won't get any angle, but whereas for inductor, since there is a J, I'll be getting an angle of 90 degrees. Right, so if I multiply these things, what I'll be getting? I'll be getting 188.5 as a magnitude, and the angle is, if I add these two, I'll get plus 35 degrees. Plus 35. Okay, so this is how you will calculate voltage drop across elements. Okay, you will use the simple formula I into Z and you replace the Z with the corresponding impedance of that element. If it is null, if it doesn't has any phasor value, you take it as 0. If it is having J, you take it as 90. If it is minus J, you should take minus 90. Okay, so now we will do one more problem, but I'll record it in the next video. I hope you have understood how to determine the circuit current, phase angle, power factor, and the power constraints. Okay.